Hey, everybody, welcome back. We have yet another fantastic episode here today. Kind of like Henry and I are calling it a pressure doubleheader, I guess, because we had Case released before this, and then now, so which is extremely high pressure, and then now we have Tony Hamilton coming on to talk about very low pressure. So
Less pressure.
or
Less
less
pressure.
pressure, yeah. And so, yeah, definitely less pressure. I think most places are less pressure. But Tony, welcome to the podcast. Thank you for coming on.
Thank you very much. Thank you for asking.
As tradition kind of goes, we like to kick off with just your background in metrology. Like it's pretty common that people just kind of stumble into our job, like myself.
Yep.
I had no idea what this was. How'd you get into metrology? How'd you get into calibration?
I was going to college to be a social studies English teacher, and things weren't going so hot, and I decided to look into the armed forces. And I went into the military and tested fairly high on their ASVAB, and they asked me to, the Navy asked me to become a Navy nuke. So I was nuclear power in the Navy. We did calibrations. They first taught me how to be an instrument tech and then how the plant operates. And it was very quality oriented. All the way down to the tech level. We all thought about, the do's and the don'ts, and
oh yeah,
always, kind of pretend that you're always being watched, so you're always doing the right thing, and always being audited. We had Airland and NAV-CO8 constantly, coming on board, and especially NAV-CO8, they had 06s that got them coffee, so they were real high-ranking people that made you sweat a lot, and it got you used to that kind of environment of oversight. And then when I got out of the Navy, I became a nuclear instrument tech at a power plant on the James River. Loved it. But my wife and I are both from Indiana, so I started looking for a job back in the Midwest. And I landed on pharmaceutical. Figure it's regulated, so it should all be good. And it was quite a bit more different than I thought. And started off as a technician, and within 6 years, I was the metrologist over pressure in their primary cal lab, and I did that until 2021. The lab itself became accredited in 2008. I was a part of that as an engineer. And so I learned the standard really well, made contacts like Dilip Shaw, and down the road, Henry here, and some of our other colleagues. And in 2021, I went and became an assessor as a sort of a side gig back in 2018, and started doing that at the beginning of 2019. And then my own quality group within the company noticed that, and that gave me a lot of clout with them. So in 2021, a position opened where I was quality assurance for the Cal Lab, and they asked me to do that, and that's what I've been doing for the last 3 years. Loving it.
Wow. Now, when they got accredited as a primary lab, so are you saying like dead weight piston gauge type standards?
No, we never. Our client base were mostly small field types of secondary standards.
Oh, okay.
And so just having like precision transducers for the bench were met 95% of what we needed to get done. So we kind of played with the idea. I've messed around and played with the DHI's PG7601 automated mass handler.
Yeah.
And I actually one of the pieces of equipment that we still currently own is a forced balance piston gauge, an 8601, which is right now it's unvalidated and we can't use it, and so there's some of our traceability concerns with really low pressure. But that one was, it's got a resolution of 1 millipascal. 100,000 Pascal sitting on top of us.
Oh yeah, I was going to say a Pascal on its own is extremely small to what we're used to in PSI, right? The average person thinks in PSI, and a Pascal is very small. Like, what is it, 5 or 6 digits?
It's so sea level is considered 101.325 kilopascal.
Yeah.
At that 0.325, you're talking about, that's the 5 is 5 pascals. And
yeah.
This machine saw a millipascal as a resolution.
So what kind of challenges, what kind of measurement challenges does that bring? Like, you can't, do you have to hold your breath in the lab?
Yes. I got good at setting up programs to do automated calibrations and data collections, and then set the timer so that it would start after everybody left at the end of the day, because doors opening and closing in the building would throw off stability pretty bad. That was always fun. Absolute mode wasn't so bad because you're going down really low in absolute pressure. We had both. I know for at least pharmaceuticals, you've got freeze dryers. In order to create a chamber that can go down to, the negative 180, 190, you've got to pull a vacuum on it. You can't do that with pressure. You're getting so low in terms of overall enthalpy that pressure itself is creating a temperature. So you've got to pull a vacuum in order to hit those low temperatures. And we'll get those 1 torr heads. Mm-hmm. So what that's a torr to a pascal was about 13.6. It's something really,
Yeah.
You've got I know that you've got 750 roughly torr sitting on top of you, and these sensors were 0 to 1 torr.
Yeah. Well, and you're very limited at that point with standards, right? I mean, it is like we had a turbo vacuum at the calibration lab I was the technical manager at, and I think it was like, and forgive me if this is wrong, like Cole Palmer or something was the only one that made the ones that we needed. But yeah, you start to run into limitations of even the standards to do it.
Well, on the reference side, we had a turbo, and they come in a lot of different flavors. They have, we were using Variant. I think they got bought by Agilent or vice versa. But I've been out of the engineering for 3 years, so sometimes I start dumping knowledge. The turbo with a dry scroll roughing pump. So we'd have a dry scroll downstream of the turbo. And it might take, we would let it stable. We would turn all the pumps on and let it stabilize for a half hour. It'd probably take more like 20 minutes, 15 to 20 minutes. But you would get down into the 100 millipascal.
That's crazy.
Yeah. And if you ever get the chance, I did this for kids' science classes. I got a hold of a vacuum plate, and I got one of these two vein oil vacuum pumps, and hooked that up. And I've got a bell jar, and I'll put a glass of water in there and take atmosphere off of the water, watch it boil at room temperature. And then as you continue to pull pressure off of that, you hit the triple point, and the ice just forms right across the top. So you've got liquid, you've got solid, and there's molecules of gas.
That's so
H2O
cool.
in there. Yeah.
Water vapor. Yeah.
So I've always, nuclear power was the opposite way. You need to achieve super high temperatures, and you're trying to do it with water. The only way you can do that is apply really high pressure. So we would operate at 3,000 plus pounds, so that the primary loop was sitting at around 700 degrees Fahrenheit, and it's still liquid. And then on the other end of things, I come over to the pharmaceutical where they're doing freeze dryers, and I'm like, oh wow, this is just the same thing, only in reverse.
Can you talk about that a little bit, like the importance of pressure? Case was on last week talking about like food packaging. You do extremely high pressure, you can take out all the bacteria and everything. So in pharmaceutical, one of the big things is the cleanest, make sure your water supply is as clean as possible. And then you get into on the pressure side, how does pressure relate to making medications for people?
Well, we do actually have high pressure applications. They were starting to make an appearance there at the end of my engineering career with the company. And we would see like 30,000 pound transducers for homogenization. So
Okay.
they needed some sort of a compound to be homogeneous throughout the what they were making, and so they would just apply super high pressure so that you would get that dissolution, I think is the right term. I'm more of a physics person background. The chemistry at the pharmaceutical was
Right.
way over my head.
Yeah. That's the Thomas Harper realm. He's a
Well,
chemical engineer.
you're modifying the molecular level at some point, right? I mean, and you have high pressure is allowing it to do that, which is really cool because it's formulation of medication that, like, the company that you work for is doing really cool stuff. There's a lot of anti-cancer research. There's a lot of recently there was a lot of COVID research, a lot of mRNA, all these other vaccines and everything else. So what's the coolest thing that you do, like being in part of pharmaceutical and stuff like that? What is one of the coolest things that you get to do?
I really enjoyed operating that force balance piston gauge, knowing that NIST had serial number 101, and that they helped design that with DH Instruments back in the day before they became Fluke, and having that there and being able to do not just the one tour heads off of freeze dryers, but also doing calibrations of one tour differential heads. So there's a whole new avenue where you want to make sure you've established a clean area for your drug manufacturing, and you have to maintain it. Well, you do that, which is the opposite of the nuclear power industry. They want to pressurize the room so that when you open the door, you get a breeze that blows any particulars or anything off of you, and you don't bring that into the room where they're manufacturing drugs. Whereas nuclear power, you didn't want any of those potential zoomies, as we called them, to come out of the containment area. So they would have usually a vacuum of some level. And you get into building construction there too on both ends, and how much differential pressure can you put on a room before you're going to start causing issues with the containment itself. You know, it's if you put 1 inch of let me back up a little bit. I absolutely, as a pressure metrologist, hate columns of liquid as a unit of measure, but they're so ubiquitous, it's kind of hard to get around them. But I think a lot of the ISO standards for the clean room stuff required like a 12 Pascal, which you get down to, like, for the HVAC people out there, that's around like 1/8 of an inch of water. And it seems like a really small amount, but it's per area. So pressure, unlike force, you've got your denominator on area. So a great big wall, it might be a very small differential pressure, but you've got to cover that whole wall. And so now you're talking hundreds of pounds when you just thought you were putting a couple inches differential on there. So it's all just being able to think outside the box and think of different types of physics that can interact and affect.
Well, I think this really rings true to people. I did a lot of on-site. And so I'm assuming over your years, you probably had people come on-site to offer third-party cal services. I mean, or am I wrong on that? Do you guys sometimes have third-party come in to do things in any of the pharmaceutical time?
Yes. They're kind of outside of the primary labs organization. A lot of the different areas. So the areas aren't required to utilize our services. They are required by the Code of Federal Regulations that govern pharmaceuticals to use traceable measurements. Nowhere does it say accredited. And so we decided that in order to meet traceable, we're going to go the extra mile and become accredited. Some areas do have third parties coming onto their site. We actually have a small team through Metler Toledo and some other groups that supply technicians that will do on-site scales and balances, which are an important facet to pretty much any industry. You've got pallets and you got to weigh them. Or you've got balances in QC labs that need to be calibrated, and you can't send those out for calibration. You can, but it doesn't really mean a whole lot because you only know what it was in their lab. You don't know how accurate or inaccurate. You got to do it on site.
Yeah,
you got to do it right there.
Gravitational constant changes.
That's right.
So that does help because you guys made an internal decision, I'm assuming, to not just the extra mile, but like you said, you can control your traceability a little bit there, and some of that quality where I was going to lead you to the question, a lot of what you're talking about with room differentials and pressure and all that, really a lot of on-site people see that every day, right? They're going into biomedical or pharmaceutical, and they might be calibrating differential gauges on the walls, and they're like, well, what does this matter, But a lot of times I think these people that go in and maybe they're not as knowledgeable don't understand how important it is. And it's important if you're going into a place like, pretty much anywhere, you're being trusted very heavily, where a place like yours, you're like, let's just control it internally, which I think is probably pretty important,
Yeah, I think it says a lot about the upper management on their thinking on that, and that you want to, not only though do you get the control by having it in house, but you also have the ability to build the internal expertise. So I don't know all the answers. There are definitely things that I get approached with on a day-to-day basis that I don't know, but I know somebody who does. And I can find that person and get those answers to those people instead of, some lone QA rep in some other area coming across a problem and either deciding this is too complicated, I'm just going to, pencil whip this, not illegally or nothing like that, but, I'm going to come up with a quick and easy answer, or I'm actually going to spend hours trying to hunt the web for an expert out there on this particular. They can call up the lab and get an answer within at worst a day or two. We've got access to companies like Henry's all over the country, and we can ask them about, I've gone into places, medical devices use force and torque, and they've got machines that are testing the resilience of the different medical devices. How many times can this thing be rotated before it breaks, and all that kind of stuff, and it's really fun to go around.
Have you ever seen those pill crush machines?
No, they're very. I've heard about them. It's very interesting. I wanted to see some of these, but I didn't check that part out. But it's very similar to like the same hardness tests that you have for like chunks of metal. Only they want to test the hardness of the pill.
Right.
Yeah. I've heard about it, and the force gauges used to do the calibrations on those devices. I think it's force, isn't it?
Yeah. Except for sometimes they come up with their own units that are really wacky. It's some sort of engineering unit that they come up with at the manufacturing level. Some of them are really odd. Do you think so? Not to go back again, but do you think also that having that internal lab, sometimes you have a little bit more ownership of what's going on there? Because I unfortunately have seen the bad. Like I've seen very clear pencil whipping, or measurements not happening. The famous they tested a full scale of vacuum where we're up here at over a mile high, and we don't have that much atmosphere to pull, right? So I've seen the bad, I've seen those things, and sometimes I feel like there's a different motivation at times, and I'm not trying to obviously get anybody mad at me in the third party cal industry, but like that ownership of the process, especially in things like that, like pharmaceutical, and you see it also in airline type stuff, right? Where they like to control a large part of that internal cal process.
Yeah, I think so. And I mean, also for pharmaceuticals, so gosh, I think it was like 2017, 2018, there was a really big push by the FDA for data integrity. So DI became the buzzword. And really, to get attention and money in the company, all you got to do is say this is related to data integrity, and you're going to get funding. They're really big on that. So it makes it, even though validation of software, even commercially available off-the-shelf software, is rather robust and difficult and timely, they really push that because of the DI, and they are more aware of what kind of risks do the different labs have. So they're really good about, so quality and operations are two separate entities. They don't have the same chain of command. So your requirement to get this line up and moving and making product and thereby money is not going to affect quality's oversight of that process, because no, we're the same company. It's completely different chain of command. I don't answer to your management. So it makes the defense of I'm going to methodically do this the right way a little bit more defendable, a little bit easier in a commercial, organization. But it also, it makes you a little bit more aware of the type of incidences, like in a cal lab. It's pharmaceutical, and so my background is not chemistry. And one of the things that I've come across here recently is in chemistry, they're all about stopping people from testing to conformity. And what that means is I pulled a sample from the water tank and I'm going to test it. Oh, and I don't like the results, so let's pull another sample. And I'm going to keep pulling samples until I pass. That's a huge
test until it passed. That's what they did with rocket. And then, Greg was on talking about the rocket testing. Same thing. Just keep testing it till it passes.
Right, exactly. That's testing to conformance. That's the best way for the FDA to come by and lock your doors.
Right.
Yeah.
And it's a lot of people that are at stake. The risk level is quite high in these situations. No one wants the lawsuit or potential lawsuit because of bad batch of drugs. So.
In a cal lab situation, it's a little bit different. As long as we're not talking about testing, we're talking about calibrations. That what I have to explain to auditors that come in to us is that the type of testing that we do is non-destructive. So if I suspect that something wasn't set up properly on a pressure calibration or any of the other calibrations, I can take that instrument back in the back and I can set it in the bath, or I can hook it up to the system and I can run it. And I expect to see within the measurement uncertainty that we've determined that the results should be the same. And if I don't, we've got a problem. Somebody didn't do it right. So the pencil whipping is more of a case of, hey, I'm a hard charger and I want respect as a tech, and I'm a new guy. I feel like I got something to prove. And all of a sudden, that individual's got, 20 items done in a single day. He's the go-to tech. Yeah, and you got to go, wait a second. There's no way you could do a conductivity test in a half hour. You got 3 test points and you're changing the conductivity and you're waiting for stability. And no, that's not it. So, yeah, there's different things to look for in terms of that sort of thing. And then also making sure that is communicated to your oversight, that quality understands that, the auditors, the regulators understand that, and they're not hitting you for, we've had issues where, the software times out. Like they're doing a calibration of a weight set, and halfway through the weight set, a weight that they've gotten in for the past 10 years fails, and they put it under a microscope and, oh, wait, there's something on this. Well, we're a pharmaceutical. That could be anything.
Oh,
the first thing we do is put it in the decontamination room with a hood, and we don't touch it. He gets back to the table, and the software's timed out. So all the weights that he's done so far, that data's lost. man, talk about getting people upset, lose data. And they
It does.
have,
Oh, yeah.
yeah, pharmaceutical, that's a big deal. So you've got to have your explanations in place. You got to understand your systems. You got to understand what other people are looking for and being able to explain that to them on why are we different. And also at the same time, keeping an open mind that they might have a scenario that you haven't planned for that you do need to keep in mind. You never want to go into the situation thinking I know more than everybody else. It's
right.
Wait and listen to what they have to say, better understand the question, and then, okay, I see what you're talking about. That really hasn't been determined as an issue here because of measurement uncertainty or, the way we performed the calibration or whatever.
Yeah. Well, you've blown my mind, Tony, because something you said in there really perked my ears, and especially like I was saying, doing as much on-site as I have. When you run that yourself, you have control over your method, which, and I never want to divulge anything, but we have a ton of people that communicate with us, when they change jobs or, when they're having their struggles at work, right? We hear about it at the school. We're here to help, right? So we hear all this stuff. And sometimes it will be people that are trying to make changes in their universe, right? Trying to improve measurements, and they'll be telling people going on site, like, hey, you should, for this, actually be taking the standard, and being told to their face, we're not taking that, it's too heavy, or we're not taking that, it's this or that, or whatever, having, that just, it really was a good point that you also have control over the method and the properness of that testing method. But your company also has you. Some of them that I've serviced doesn't have anyone really competent in metrology, so it's kind of a if or that type situation there.
It's tough.
Yeah, unfortunately,
it's really tough.
Yeah,
there's not enough experts out there. It's kind of like doctors, right? Our population is growing. Right? Seriously, our population is growing. Yeah. There's a need for more measurements. There's a need for more doctors. Anybody that's tried to get one in some places know that the wait times, if you need a specialist, are high. And metrology is virtually the same way because we're not training as many people that are needed. Mm-hmm. And thankfully, there's the school, the sign, and some other avenues out there for some training. But you're not going to replace, like Tony's an author of the Metrology Handbook too on pressure that I have pulled up. You're just not going to replace people, the experience and knowledge base out there. I mean, there's good people out there that can learn, but then it becomes an experience thing. Oh, this gauge you have to do this to. The weights that if you have this, it's going to time out on you. You don't want that. I mean, some people write that into the procedures. It's still difficult. Just trying to go back to day one of when you start looking at all this measurements and it clicks. It takes a while. I mean, day one, you go into the lab. It's not like you're a pressure expert on day one. You're going to shadow someone. How'd you learn, Tony? You shadowed somebody, just come in and start doing it?
I was a process technician, and so I would perform usually, with multimeters, electrical calibrations of electrical systems and making sure that the voltages at the right points are at the right levels and within spec. Once in a while, we would pull out the decade box because we couldn't get to the RTD that was in the loop. That was like a once in every 10 years evolution. When you check the actual RTD, you would disconnect the wire from the RTD because you couldn't remove it, and you would hook it up to a decade box. And just, seeing that stuff at first, it's just kind of hey, this is what they want me to do. Nuclear power has had, and I'm sure still does, awesome procedures. And the training. When I got hired, so I spent 6 years in the Navy, 2 years of it training, 4 years on a ship. And when I got out as a qualified reactor operator, shutdown reactor operator, and reactor technician, I still spent greater than 6 months in the training facility before I ever had a badge and could go into the plant. It was classroom. we had full mock-ups of a lot of our work and stuff. So we would, it was for radiation, for working around radioactive areas, it was time distance shielding. And how do you reduce the time? By being very skilled at a job that almost never gets done. And the only way you can get that experience is by a mock-up in an area that's not radioactive. So you have chances to make mistakes. Oh yeah, I forgot this one tool. I got to go back and get this. Oh, this is how this is hooked up. Oh, this is the type of special screwdriver I need to get the plate off. I'm going to, the shielding involved, you'd have a lot of lead plates. So you'd have to have the hoists and bring that into the job site. You just, they were very mindful of your time, and they didn't mind spending a little extra money training you to the degree that's needed. And, talking about the training part of it, if you look back at American industry at post-World War II, we were geared to make automobiles. We made automobiles in the 40s and the 50s and the 60s. The 60s hit, and you got JFK talking about we're going to go to the moon, which we did in 10 years, less than 10 years after making the speech. And in order to do that, measurement science, I think it was on the order of 10 to the second power in accuracy of improvement that was necessary to hit a target like the moon from 200,000 miles away, escape the Earth's gravity and hit there. And that is not just true for space. That's true for every endeavor that we have. At the pharmaceutical level, being able to, I read a story the other day that they had I forget how old the child was. I think it was like a year old, born with a defect that it could not hear. And through a genetic cure, they were able to reestablish that kid's hearing. We're looking at being able to reverse all kinds of diseases, not just diseases that you pick up, but diseases that you're actually born with because your body didn't replicate the DNA the correct way.
Right.
And in order to do that, just like hitting the moon or hitting Mars, you need better measurements. And I don't know how many times, I talked earlier, you were, Ryan, you brought up having some of your pressure equipment behind you and bringing in some of the higher precision pressure stuff. And that's all we really needed for a lot of our stuff. But sometimes I would find areas that thought, what, I'm going to spend $20,000 on a piece of equipment like that instead of getting, like 20 $1,500 modules so that I'm doing the right cal with the right instrument. I'm going to make it easier on my techs. I'm going to buy one unit and I'm going to be able to test everything in our facility with it. And it's like in order to do that, you had to buy state of the art and you didn't explain to your technicians how to use it. You get one of those, I'll go back in time a little bit, PPCs from DH Instruments. You can put in the head height. So it'll automatically compensate for the difference between where the reference standard is and the instrument. I found no tech that even knew that existed.
Right.
You can't just buy the greatest and think that people are going to automatically know how to use it. Right. If anything, they're going to know less. A mic, a kid can figure out a micrometer. It takes a little bit of practice and a little bit of playing around, but it's a fairly, straightforward, simple design. Put a whole number pad and a whole bunch of other little buttons on the front. Good luck. Wow, that's capable of doing head height discrimination. Now, yeah. Did you know that? Do you have a measurement? Do you have an instrument that can measure the differential height? Talking about the clean rooms and the really small, 1/8 inch of water differential pressures and their quality, who didn't know squat about instrumentation and calibration, were saying you have to calibrate that probe in place. You have to leave it up there in the false ceiling. And so they had like a PPC3 sitting on a cart with a vacuum pump on the bottom and a tank of gas, a compressed gas on there, nitrogen, and 6 feet of hoses exposed to the environment, doing a small differential pressure. And I'm like, I don't know how you ever got it to pass.
Ran it till
from
it
my
passed,
experience,
maybe.
well, or it did. It never really did.
Maybe, yeah, it never really did. Well, hey, I got it. It's one time. Let's test it till we get the answer we want.
They got it set up so that it's testing a pressure that it thinks is like 5 feet lower. And that's a small amount. I was doing tanks that were like, it was like 3 floors up, and so we would just do the math on 30 feet or whatever it was, because we were doing 0 to 100 pounds or a couple 100 pounds of pressure, and this is the only place we could do the test at, so we'd hook up there and then do the pressure somewhere else and just do a compensation equation to figure it all out. And we give people the tool to be able to do that calculation for them, and they don't even know that the tool is embedded in the device. So and nobody's taught them that they do need to account for head height. I had an engineer tell me that we don't have to do that because we have the low and the high connected. And I was like,
Oh
what?
my goodness!
This isn't a 4-wire RTD where you erase essentially the
And automatically
resistance of your
corrects.
Yeah. I'm like, what? You're a degreed engineer? What college did you go to?
Tony, you're hitting on some interesting points here, because you mentioned this, and there are two things: engineering that has no concept of metrology or the science of measurement, and quality personnel that are in companies that have no idea of the measurement either. They just want to see X number, or there's all kinds of statistical tools in quality and everything else. That's really interesting, because it seems that there's a large disconnect a lot of times. And I've been on the phone several times where quality is against engineering, where the tech is against quality. It's like quality's breathing down our neck, or engineering's bringing down our neck. I'm just going to let them do it and fail, because I'm the tech and I know that what they're doing is stupid and what they're asking me to do is dumb. And I hate that attitude too, but there's a lot of techs out there that their voices aren't heard and they're being overshadowed by engineering quality.
Like,
and I think
a lot of
it's
times,
really sad.
Sorry, Henry. Just one small thing to add in there. Sometimes they're the only person in that facility that understands these things. So
The tech. Yep.
Yeah.
They are, a lot of times. Yeah.
Yep.
And, quality's got the power, and engineering thinks that they've got the power. And it becomes a 3-way fight in the same company. I hate that. You can't, companies come and go, and through no fault of their own, you're destined for failure if the people within your company are at war with each other, and that kind of us versus them. And Philip was really big with me on. There was a conversation we had a while back when I went into quality, and he was like, "You need to address. Yeah, I'm sure that your company is no different than most others. It's siloed. There's engineering, there's operations, and there's quality."
Mm-hmm.
And he was right. I was like, oh yeah, back in the day when I was the nuclear power, engineering knew as much about what was needed in quality, would anticipate, quality's not going to go for this.
Well,
Whereas now it seems I need to just understand engineering, and I'm going to do what quality lets me get away with. And it's
Right.
like,
That's so true, though.
catch me if you can, and I'm just like,
Still it
You
is.
did have, and the problem is your company's reputation's on the line when you do that.
Mm-hmm.
Yeah.
All it
exactly.
takes is some bad customers or bad press. You do something, you don't account for something. Nobody's out here trying to kill a bunch of people, but bad decisions do lead to loss. Sometimes it's just product loss. Our product is a lot of money. I would hate to be the cause for it. My salary ain't going to cover very much.
Yeah.
But, and in terms of force, you got bridges falling down because they're aged and they weren't tested properly, or they weren't built properly. They didn't test the force strength of the materials used or whatever. It can come down to that.
Gusset plates that are too small in the case of the Minnesota collapse. You got a lot.
Yeah. I don't know of any pencil companies that are $1 trillion companies. There's no real danger there. Your pencil works. Oh, it doesn't? Okay, get another pencil. But medication needs to work every time, all the time. If it doesn't do enough, then you end up suffering more from the disease that you're trying to ward it off against. And if it's overprescribed, then that causes problems too.
So true. Hey, you were in the Navy, so I was reading the recent issue of Quality Magazine, and they were talking about the thresher. Do you know that story?
Oh, yeah. The thresher.
Yep. The story.
There was
100 people. Quality and safety existed, but I think the parts were not up to certain specifications, and they let it go anyway. And the sub sank, killing more than 100 people on board. I'm doing this from a bit of recollection. So, but that started the sub-safe program, right? Yeah. So out of something that's bad comes something that's really good for the betterment of society. And Henry Petrosky had these comments about companies, and when they get complacent is the worst point in time. Because complacency is dangerous. It's worked, and we're talking engineering quality. It's worked this way for 20 years. It's going to continue to work. And you brought up bridges, and that's just one of the main things that's happening here is as they age and deteriorate, they work fine for 20 years. That doesn't mean they're going to work for the next 20. There's been loads on them, forces on them, things on them that people did not anticipate. Maybe the engineers back in the day anticipated climate that's a big in the news now. They anticipated the climate was going to be this, the actual weather conditions were going to be that, and things have changed in areas. It's warmer and all that. So we don't know, a lot of times we do not know the foundational pieces in which people built something at that time. Records, there's documentation, right? Well, but we don't know the assumptions.
Well, and if you identify, so I'm so glad you brought this up, Henry, because this is a hot topic with people that are chatting with me right now that are managers, but they're middle management, right? And they're bringing up legitimate things that are like, they're assessors and things of that nature, and they're bringing up things, and the places are like, we 20 years, we've never had anyone bring any of that up. And it's like, so I am now, like, why not change for, I don't understand that mentality that like, oh, no one's brought it up till this point. It drives me nuts.
I can tell you some of it. Some of it with some owners I've talked about is like, I have 5 years to retirement. I just want to sell my company to one of the bigger people out there. And I'm just going to let this go. I'm making money and just let me get by for the next 5 years. There's very much some of that in the aging population. Right. Some of the other
ones. That's a very similar attitude about selling your house. Do I need to fix the floors before I sell it, or do I just let them take care of it type of an idea? That's me and the wife were just talking about that. That's a very parallel. Not everybody has a company that they own. They can understand that level, but that we do that. We
the brakes are going out on my car.
Exactly.
Yeah.
Exactly.
Oh, it's good. It's past inspection. It just made it by. The guy said the mechanic, the Galler guy at the mechanic place says, "Look, this is meeting the minimum criteria to pass and squeaking and all that." And he said, "Okay, I'm good. I'm good for a year."
You brought up complacency. That's a huge one. Yeah. But I would also put in arrogance. There's a reason. There's a reason why Chernobyl blew up. Arrogance. Yep. We know everything there is to know about this plant, and we can do this. Mm-hmm. Boom.
That was management.
I guess not.
Mm-hmm. And they were
and bureaucrats making the decision instead of scientists who know the system even better. Well, we need you to stay online, stay on operation, don't shut down. Wait a second.
Deepwater Horizon.
We weren't.
Example. Yeah, we don't want to do this. This test is expensive. We're losing time. We want to, we should be okay. Well,
you brought up the thresher. right?
Yeah.
There were two that they taught me about in school, and I'm going from very old memory. These are plus 20 years, plus actually, man, I joined in 91 and got out in 97. So the director, they were doing test depth.
Yep.
So they weren't going to test depth. They were just doing tests at really low depths of the ocean. And they were in radio communications with the surface fleet. And they had a scram of the reactor. I don't remember why the reactor scrammed, but a reactor scram is a protective feature so that it doesn't blow up like Chernobyl. Blow up, not like a bomb blow up, but, bad things happen.
Yeah.
So they did not at the time have the immediate action to close the steam stops. So their steam generators, the valves were open, the steam was escaping, and they were at a much lower depth than they're ever used to running, and their electric propulsion. So they've got and you can imagine just rows and rows of car batteries hooked up in series and parallel in such a way that they could move a shaft on a boat, right? A big one. And it wasn't enough. They're too far of a depth. The water's too dense, too cold. They're still thinking. They're still going lower. And from what I heard, the surface fleet heard them, heard the screams, heard the cracking of the hull. When they went to try to bring the reactor back online, or at least use what steam was left, it had all blown out the steam generators. There wasn't enough of that to engage the propulsion, and they continued, and they discovered what the crush depth really was.
Wow.
Yeah, I just pulled it up here. Yep, the backup generator broke. It got to 140 degrees Fahrenheit after about 10 hours. They were just, everybody was depleted, and it's not
all of us nukes when we got done with prototype. When we learned how to operate an actual reactor, they would come and ask us, "Do you want to be submarine fleet?" At 6'2", and at the time I was a lot lighter than I am now. I was probably 260, maybe 270. I'm a few dozen pounds heavier than that now. I was like, absolutely not, unless you could put me on a boomer, because those were big. And you just go to the bottom of some area and do a patrol of some part of the ocean and wait for the call to start Armageddon.
Right. Yeah,
Launch the ICBMs.
I deployed on a normal ship, and it was tight quarters. I couldn't imagine it being.
Now, I ended up on a carrier. It was great. Loved it.
You had all the room on there as opposed. Here's the Petrosky quote. I pulled it up so everybody can hear it. Failures appear to be inevitable in the wake of prolonged success, which encourages lower margins of safety. Engineers and the companies who employ them tend to get complacent when things are good. They worry less and may not take the right preventative actions. So, that piece of equipment that you want or the tech wants, no, don't need it, right? We don't need to do this. Let's just keep pushing and pushing, and we'll make more money, and then we get more money, and eventually we'll buy it. So
there are several people that I interact with at my company, and usually when we are discussing a deviation that occurred and how we're going to remedy it, I get a lot of times the head shake back and forth, and we're spending too much time analyzing these one-off. And I'm like, well, keep track of how much time you're spending on the one-off, because you did 10 items yesterday. You reviewed stuff that was very straightforward, passed, no issues. You got them done in a hurry. And then you hit this one oddball that caused you to come talk to me. If we can get it so that this is no longer an oddball, that's what reduces the time that you spend with it.
Yeah.
With this one-off, this is the weird thing. And it's just the upfront cost of dealing with a complex world.
Or do you need that, Tony? That's the other thing. That oddball, maybe someone in engineering or quality bought it because it was the lowest. Maybe there's something else out there that's far more easier to use. There's so many answers to a lot of these problems, and people get stuck in this box of make it work, right? And I think that's what you're talking about somewhat. And sometimes, with the process, you make it work. It's a lot easier for the techs, but there's other times where there's something else that's out there that might cost a little more, though it's going to save you so much money in the long run because you won't have this weird stuff. One of the better examples is NASA designed this passive torque latch, and they could have bought something commercial. They paid all this money for this thing that needed jigs and rigs and everything else. And how many people in space are really going to need the special equipment to open the door? It's there anyway. Like I'm saying, you could have something commercial. They could have bought something commercial off the shelf instead of spending millions on this passive latching system. But people do it. Or they buy something that they think they get a good deal on, and then let's figure out how to make it work.
You got to
I'm not saying that's it. I'm just saying that happens.
Especially the salaried individuals that you got working for you. You got to give them breathing room to be nerds. I am a nerd. I love it. I love what I do. If you leave me alone, I'm going to occupy my mind with something scientific. I'm going to get on the internet and I'm going to start looking at some of these things that you're talking about. And that's who you want. You want to promote that behavior, because that, when you are faced with a new type of engineering process that you have no understanding of, I see it too. People they think that they're all alone and by themselves, and they've got to figure out how to fix this. And it's like, there are other industries that I bet solved this issue 25 years ago. And you can piggyback on that. You can take advantage of the fact that they've learned so much. You just need to get out there. Nuclear power and pharmaceutical, they don't seem to have anything related, except that they almost seem to be mirror opposites of each other. So when you run into a high pressure over in pharmaceutical, go to nuclear power and see what they have to say. Our clean rooms worked in reverse, but they still had to measure differential pressure. You just hooked the high and the lows to different parts of the building. That's all. And they probably have, I think, it's been so long, I don't want to say anything that might not be true, but I was thinking that we had like some sort of fairly rudimentary airflow device that, as long as there was enough airflow between the two rooms of differential pressure, then they knew, they had done the math and they figured that the pressure in the room that they wanted to have the pressure was high enough to perform activities there. And they didn't rely on DP because DP is so hard to calibrate. If you want to do an inch of water calibration, not only do you need to hook up the high and the low sides to isolate yourself from this ever-moving barometric pressure target. It's not 101.325 kilopascal. It's all over the place, and it depends on your elevation. Here in central Indiana, I'm at 98.8 nominally, because I'm at about 720 feet elevation. Just that 720 feet makes a big difference. Over in Denver, because I've done assessments over to the north of Denver, because I've done a lot of flow, and they like to pick me as the assessor for flow instruments. So I get to do flow. And right there in their lab, they've got a barometric pressure dial, and I look over it, it's sitting at 12 pounds. I was like, 12 pounds? What's going on? They're like, oh, that's nominal for 5,200 foot elevation. I'm like, wow.
Yeah, that's what I see.
The
here.
Mountains are over there. I'm not on a mountain. Yeah, but there's a bulge in the center of the continent, and you're about 5,200 feet above sea level.
And that's not even that high, considering some of the places like in Peru and what's the one?
You really have to open up. You not only can you just put the highest dollar equipment in the hands of your techs, you got to provide them with the training, and you got to crack the manual. Yeah. If you're going to spend high dollar on stuff, chances are a lot of that money is in the publishing, the research that it took to develop that product. And the company, in most cases, has put together excellent ops manuals. You look at a pressure ops manual from some of our leading providers, and they'll tell you, just like there's an operating temperature envelope, so you don't want to be using, we haven't done an analysis of this device's uncertainty below 15 degrees Celsius or above 30 degrees Celsius, right?
Mhm.
A lot of them will say, we haven't done a study on greater than 2,000 meters or something to that effect. And they're talking directly to labs that are on unusual elevations.
Right. Yeah, I love it.
And if you never crack the book, you don't know that. And you're like, hey, I live in a big city. So what if we're at 5,200 feet? What's that going to do? And you buy it and you set it up and you think it's going to work. And it does. When you send it in for cal, it works because it's being calibrated at sea level in a well-conditioned room,
Right.
low humidity.
Yeah.
And it goes back to your lab, and who knows where it's at? Who knows how accurate or inaccurate it is?
And it happens all the time.
Yep. You didn't look at the operating ranges and specifications on that. So many times I talk with people about calibration specifications. A lot of times we are saying, hey, number one, our lab is not allowed to do work on equipment because you just turned it in. We're never going to hit the, I believe in manufacturer specs.
Mhm.
We want to know, you handed me a temperature probe, where do you use it? And that's where I'm going to test it. It might be rated for negative 195 up to 200 degrees Fahrenheit or Celsius, but you don't care if it fails at negative 195 if you never use it there.
Right.
If you never go below negative 40, why are you testing it down there? You just like to hear, you like to see deviations that I write for you? I mean, what's the upside?
They do it
here?
all the time. Or they have.
Oh yeah, because it's easier.
Yeah,
I can write manufacturer specs. They can write that, but if they don't write anything, we can't accept the cal. We wait until we have confirmation on what they want. And specs too. I work with a lot of different shops around the company, and their lead technicians and stuff call me up and say, hey, we just bought a new multimeter. What should I put the specs at? And I'm like, well, if you don't know, if you aren't given specs on the equipment that you're calibrating, then I think you should probably play it safe with 2 times. Make the manufacturer spec an adjustment limit. And
Right.
so if we have to send it in, they'll always keep it to that. And if you really don't need, the 0.01% of reading, then why make it that? If the stuff you're calibrating is 0.5% of reading, then, no reason to let you know that it was out of that 0.01. 0.02, I'm still, 20 times to 1.
I have to share one with you both that I had the other day. It was one of the funnier ones and one of the sadder things I've ever heard. Is the person unnamed says we just need a 4-to-1, and so we said, what do you want? And it's like, well, make it 2, 5, 10, doesn't matter as long as it's 4-to-1. I was just like, word on this. Do they know what they're doing? This is a major problem. And so apparently their requirement is they just want something on the statement that says 4-to-1. Well, to me, they didn't even understand accuracy at this point, what it was.
Right.
Even in manufacturer specification would have been better than what we heard. We heard, give me something that ensures I can say I got a 4-to-1. And that, is this the 90s again or something? Because this is insane.
That's usually that a TUR of 4-to-1 is generally the what a lot of folks operate on.
Yeah, but it's
in
all
quality.
The
one thing that they know from instrumentation is I need a 4-to-1 accuracy.
I don't even know why they think they need that. I have no idea.
I've shown mathematically what a 1-to-1 will do. A 1-to-1's fine. I can do 1-to-1 all day. You just need to understand something. Just because it passed that spec doesn't mean that that's the accuracy that you're getting from that meter. And that tends to be the hardest thing to get past lay people. And that seems to be, lay people is now the term I use for everyone who's not a metrologist.
Right.
Right. Oh, it makes sense. I mean, I'm not a big 1-to-1 believer because I know the inherent risk, your PFAs and PFRs, how high they can get, and the ability to make a bad decision, the wrong decision increases exponentially. And I'm also trying to say, hey, we talked earlier, if you don't know what you need to buy, I tell people err on the side of buying the best equipment you can, because it's better than having $40,000 to $1 million in scrap or huge recalls or anything else. But that also assumes the technician needs to know how to use it. Paul Reese was on talking about the Spirit of Kansas stealth bomber that went down because it's a procedure. They didn't know about the pitot tubes and how to handle those. So there's a lot going on. And then 4-to-1 is, to me, Paul Reese did a paper that said, hey, you can control, no matter what your end of period reliability is, if you're 4.6-to-1, you can control your risk, your PFA to less than 2%. No, that magic number is 4.6-to-1. It's not 4-to-1. And these people get so hell-bent on that ratio of that 4-to-1. And I don't know if that guy the other day that we talked, I don't think they understand what it means. I think it's just a requirement somewhere, and the training is weak.
So my kids, I've got my son graduated from Purdue last spring with a math major, chemistry major. My daughter here, who you might hear in the background, she's math major. They passed me up in middle school. I don't have calc. I have pre-calc, but statistics is what we use. And I have yet to hear a good explanation on how a TUR of any number, I don't care if it's 100-to-1, if the error equals the pass-fail criteria, you got a 50-50 chance that you're wrong.
On the tolerance.
Period.
Yeah.
Unless so I don't even, I like to save the best for last. So when I'm talking to another engineer and we're talking about specifications and things like that, I tell them, there's nothing inherently wrong with the 1-to-1 calibration. And I put it up on the dry erase board, and I was like, just imagine that all the other uncertainties are insignificant. Resolution, environment, the tech, it's all a wash. The only things that really matter are your pass-fail criteria. So we'll say plus or minus 1, and your reference to your measurement uncertainty that you're getting is 0.25. So that you've got a 4-to-1 here. You've got your tolerance over your measurement uncertainty is 4-to-1. So let's do the math. Those are both contributors to your budget. Your pass-fail criteria, you're not analyzing to know where that error falls. And by the gum, that means it's rectangular. So it's 1 divided by the square root of 3. Square it and add it to the 0.25, which they said is K equals 2. So you can divide that by 2, square that, and then take the square root of that sum. What do you get? You get 1.5. So you bought an instrument that you think is accurate to plus or minus 1, but when you use it, you have to understand that the accuracy, the uncertainty that you, by using it, is 1.5. So it's 50% higher.
Mm-hmm. Whatever works out to be.
And forget the fact that it's probably going to be found out of tolerance most of the time because it's a 1-to-1. But
you get a ratio. That's the fun part of the curve where your probability of false accept goes way down because you're rejecting everything because your equipment is the certain equipment is so high. So it's just all you do is just reject all day long. Fail.
Some of these measurements though that I get into where we're dealing with, when we're making measurements down in less than a Pascal, and the accuracies are in the millipascal, really all you can get is a 1-to-1 in most situations. And you have to deal with that. Yeah,
sometimes that's all you can get.
Yep.
If you can get better, I'm
sure a lot of calibrations that NASA has, or NIST for that matter, I subscribe to NIST and I see some of the projects that they're coming up with, some of the, the Kibble balance and some of these things. I am sure that equipment, some of the sensors involved with these measurements are some of the most accurate sensors in the world. How do you find anything accurate enough to get a 4-to-1 or 5-to-1?
You don't.
Forget about it.
You don't. Yeah. You just do enough sampling, enough testing, and they do in comparison. The thing that separates this from the rest of us is they get to be part of the CIPM where they can do comparisons with other NMIs. So in that, they can kind of validate. The people here, I would say, yeah, the ratios that we're talking about. So, Tony, yeah, it's location of the measurement. I mean, there's two risk profiles. People can read our risk document that we put out and go into it. But yeah, if you're either under bench level specific risk, where if you're at the tolerance level, no matter what, it's you're gonna have 50% risk. If you're using a global model, now you're based on averages, so that's a whole different ballgame and story. But yeah, just to clarify that piece on the specific bench level measurement, it is really about that, and it is for both, but the location of the measurement is so crucial, and people forget about that. People forget that the 4-to-1, these ratios, assumes that all bias has been eliminated, right? They magically put these numbers into play without like knowing all of the statistical assumptions, and some know it. Like, you know, we go talk to some people, they know everything. And then you go talk to other people, they know, like, all they know is they need the 4-to-1. And there's such a disparity between the people that get it, know it, and the people that have no clue. And they don't make it easy, right? It's buried. That bias thing, it's buried. So the first time I saw it was an introduction to statistics and metrology. I think it's section 5.2 in that book, because I reference it a lot. And I may be wrong in the section, but it does say that it assumes that all inherent biases have been removed when we're looking at the TUR. I've been corrected. We think they're corrected. So
we've done a lot of talking back and forth, you and I, over the years, and I have found with the people that I interact with, it's best to lead with a carrot. So what I have tried to do is promote good behavior. And so so you start talking about measurement uncertainty, and the eyes kind of glaze over and their mouth slowly opens, and you might as well be talking, I don't know, 12th century French art or something. But you could bring up specific issues. So a lot of times I'm getting conversations when instruments were found out of tolerance. What does this mean? And I've had key people come back and go, hey, they found it out of tolerance, but it says here that they adjusted it and now it meets the spec. So we're good to keep using this. And I was like, yeah, but did you do an impact analysis on what issues you caused? What did you touch with this instrument? Because that's going to be possibly out of tolerance as well. Now, as long as you're getting more and more accurate as you go up the chain, the likelihood of that it gets lower and lower. But you still, and I said, if you just take a second to really understand the measurement uncertainty. We had a torque wrench, so it had gone out to this one lab all the time, and they're accredited. They provided measurement uncertainty. And this one time it comes back. The metrologist reviewing the work didn't notice this. Everything passed, and he signed off on it and sent it back to the customer. And the customer gets it, and lo and behold, the quality rep saw this and saw the measurement uncertainty was now quite a bit higher than it had been on previous calibrations. And he was like, "Hey, now we're no longer 3-to-1. We're down to almost 1-to-1 on this ratio, which we passed." And I'm like, "Okay, lucky for you. That's great." But you're right. This has jumped up. So I call up the company who did the cal, and so they're using, I think it was an ANSI standard on torques, where they had to do a minimum of 3 repetitions on each test point, and that measurement uncertainty jumped because the variability of that torque wrench has changed. And it's like, oh, it's magic. It makes sense. Your measurement uncertainty went up. Their process didn't change. So the only thing that changed is the torque wrench. It averaged out to equal the torque tester that they were using against it, but the measurement uncertainty grew. That means that the variability of this thing grew over time. And on top of that, when you send your tech out on the field to put a certain amount of torque on a bolt, you have no idea, because that's a single point use. You don't know if you got the high end, the low end, or somewhere in the middle. Yeah. You need to scrap it. You need to have a spec on the maximum measurement uncertainty that you can handle. And I was like, I still had a copy of the ASTM on precision balances and comparators. And in there, they talk about what is the maximum measurement uncertainty in order to call this a class 2 weight. The measurement uncertainty cannot be greater than 1/3 of the maximum permissible error.
Yep.
I'm like, this is genius. We could use this. That adage, Dilip would always say it. If I write a contract with you that says that you're going to calibrate this while you stand on your head at noon with a sandwich in one hand, then you got to do that. Yeah, hopping on a leg or whatever. You got to do that. And this falls right into that. You now understand the importance of measurement uncertainty, especially when it comes in play on why did my instrument fail? Yeah, and now you could sit there and dictate, I don't want the test. I don't want your as found calibration. I'll send it to somebody else. I understand that the CMC is your best, but I can't allow your measurement uncertainty to quadruple. Mm-hmm. I can't allow maybe you can't allow it to double. And for a lot of stuff out there, electrical cows, you don't expect the MU to be much different than the CMC. But on a dimensional, I've seen plenty of times good labs will 3 times the CMC. That's typical.
Sometimes you'll have a technician that just brand new and they pick up the wrong standard, right? And when they put it into their software, it calculates it out, and all of a sudden you got a horrible uncertainty.
Well, let's look at that.
If you're really doing that, if you're doing your Welch-Satterthwaite equation, the determination of your K for 95%, like ILAC P14 tells you to, man, if we'll all fall on the same page and follow the exact same rule, you could look historically back at every calibration of each piece of equipment, and when you have a failure, when you have something bad happen, you can look at that in view, and it's actually going to tell you something. Just imagine if you have, like your seats, I think, Henry, they report the actual K value. No one else does that. I've never found another lab. They always assume K equals 2. K does not equal 2. K equals 2 on a CNC because you got the ability to do 30 plus tests. So you can make your 1 or 2 type A's 30 tests or 40 tests or whatever. But when you're calibrating, you don't want to spend a half hour on a single test point. You want to go and move on. And if just pick one test point on a pressure, pick your highest. I'm going to test 0 to 100 pounds. At 100 pounds, do it 3 times. If it repeats really well, you know what your CMC value is. So if the standard deviation is quite a bit less than that, then you could stop there with 2 degrees of freedom, and it's not going to change your K value. But holy cow, if that repeatability is equal to or greater than the CMC value, you're going to have K equals 3. You're going to have K equals 2.5 at least. And to see that should trigger some eyes to go, what are we doing?
Well, we're talking a lot about the denominator. If we're going to do a TUR reference, which is going to have your calibration measurement capability and the contributions to the UT. So for people out there, that's going to be the resolution of the instrument and typically the repeatability instrument. So if you have a crappy instrument that doesn't repeat real well, it's that all of a sudden that denominator becomes larger and the ratio goes down. Now, Tony, what you were saying, the P14, the requirement is to report a K factor for 95% probability. This is one that I'm still still in amazement on, because a lot of people, they still use root some square. NIST technical note, NIST hasn't rewritten that, and the GUM highly recommends using the Welch-Satterthwaite, because if I only make 2 measurements,
one degree of freedom. One.
And the coverage factor for one is what? It's 12 off the top of my head.
Well, for 2 sigma, it's like 12 point something or other. For 1 sigma, it's like almost 2. But if you're doing it, so if you're using the formula the way the GUM describes in it's 101, I think, where they talk about the Welch-Satterthwaite. So each one of those T's is, so the uncertainty that you should be putting in there is 1 sigma. Therefore, the degrees of freedom multiplier should be 1 sigma. But you don't have to deal with that until you get to the end. All you do is put in how many degrees of freedom you've got. And then at the end, based on the uncertainty, then and the combined degrees of freedom, the effective, that's what it is.
The effective
degrees of freedom.
So yeah, the Wellsather will calculate what your T value is. Yeah. And what the weight is, I mean, this gets into a big thing too, because if the weight of something, if you only have two measurements and they're not good, that can really impact what the calculation's going to be. I mean, if things repeat perfectly, you could get something different.
Exactly.
I've had measurements when I do like some training. I've had measurements where when we put in the repeatability study, the uncertainty gets worse. Or actually, the uncertainty gets worse than when you pull it out, and it's all dependent on the like what goes in there. I've had some where my stability's large, and I only have two repeatability numbers for repeatability. That the uncertainty could be less than if the stability. It's how it all works together. It's a really, until people visually like put this whole concept together and put the numbers in to it. So you were talking about what people do. It's another good conversation is when something fails. Are they analyzing reliability? Because that's something that the older I get, the wiser I get with this. And it's more about reliability than anything else of what we're doing. We're making measurements, but we want to know that equipment, how good that equipment actually is. And if it's holding up. I mean, you have consequences where techs will drop something and break something. So assuming everything is kept in ideal condition, if you have a failure, there should be a big question on why. Is this a manufacturing problem? Let me look at a whole pool of like instruments and see what my percentage of failures are. And I think that's one of the things that some do really well, like NASA, and some of the other companies out there have no clue. I mean, we've even heard that some companies, Cal Labs, are trying to calculate end of period reliability for their customers, which is, it can be done, I guess, if you have a large enough sample and a pool, though it's one of those things that it can be very difficult because you don't know the use. I did a paper on this with load cells, and I had to scrub so much data away. We had stuff that just wasn't, and I was like, I have to find all these like instruments, right, with like indicators. And then I had to go back and look at notes. Like the technician said, did they switch this? Or it looks like somebody wrenched on this. And it was like, okay, so then we started getting into, let's look at historical instruments that we know the customer base has taken care of that and had, several years. So yeah, it's a difficult, on the Cal Lab side, it's at least in the mechanical discipline, it's real difficult to do. But for people, I think they're also struggling with this a lot. And that is that calculation of, how good reliability, and what should I do if it fails? Should I shorten the date? Yeah. Should I raise the tolerance? There's so many tools that are at your disposal.
I've been in meetings where a bunch of engineers are sitting there, like I think it was humidity, and it was found out a tolerance by this much in this direction. So everything we touched is actually lower by this amount in this direction. I'm like, you're playing a dangerous game. All it takes is one screw up and you're 180 degrees out from where you probably should have been. I said, what you need to be looking at is your system was set up for this much uncertainty, and you went and tested it and found that it was this much uncertainty. So how does that affect your overall system? And if you don't know, then you need to get to a place where you do know. And that way you can plug that in and go, okay, so it's not as accurate as we thought it was, but there's no impact overall because that was just a really small contributor. Or, oh my gosh, we need to retest this, or we need to recall this product or something along those lines because we just don't know. This has put doubt into our process, and we don't know, our product is our name. And so if we don't know what's out there, maybe we should play it safe. If anything, I thought that, when we would lose a pallet of medication because somebody didn't, fill the paperwork out right, I was like, man, that sounds kind of crappy. But, it's not a complete loss. Companies are able to recoup that. You can do testing on that. We'll have medication that fails batch disposition. And then they use that in the technical, I forget the name of it. We've got a special name for it. where they do testing. Well, let's take some of this medication and we know that in order to store it, it needs to be kept in an envelope at temperature like this. Let's store it at the low end or at the high end and play with that. And maybe you learn more about the substance, but you just can't sell it to somebody to inject,
Yeah.
So,
yeah. I mean, there's a lot of cool stuff, and metrology is really cool. And there's a lot, it's just cool. And when you're into it and the things that happen, as far as the one thing is that we see a lot of is people discount stability in their survey budget.
Mm-hmm.
And that's something that no one out there, that's drift stability.
Yeah.
I buy something from somebody, this is the specification, but you rarely see that specification says, right, 1 year, 2 years. Flip does a good job with
That's
it.
standard, yeah.
There's a lot of it, yeah.
If
So
it's a standard
you
company,
get-
sometimes they'll do that.
Yeah,
That's
if
a
it's
really
electrical,
good-
I see it in electrical a lot, and where they have that, but not all the parameters have that. The ones that we're talking about, and pressure, I do not think. Speaking of Tony and you, Ryan, I don't think pressure has that. I know Foresight.
When it comes to buying pressure, so we just underwent some purchasing of new precision transducer equipment, and the
Right.
first batch that we got was crap. It was horrible. It wasn't repeatable. The repeatability on it, just from our own study. So we went to another cal lab that had a piston gauge capable of doing the calibrations. And we said, I don't want you to calibrate it. I want you to go to these points and let's do 30 repeats. I want to see how repeatable this thing is. And it did not meet, if you look at their tech notes and what they say those instruments were capable of, it didn't meet the repeatability spec. If it can't meet the repeatability spec, oh man, what else is it not going to meet? That means it's got to be tighter on the drift, tighter on some other application, and you're not going to get that.
Nope.
Yeah. So acceptance. I'm going to buy something. I'm going to spend a lot of money on it. Man, do a repeatability study on it before you accept it, or put that into the contract before
talk
I
about
actually lay
acceptance
down
criteria.
$100,000 on this much equipment and a potential to buy more down the road. Have acceptance criteria. It's not just that it passed a cow. Anything, if you take averages, a lot more stuff passes. What until, let's say, my head's in an oven and my feet are in a freezer,
Yep.
and I'm perfect.
On average, I'm fine.
Average, I'm fine.
Yep.
You're dead
Gentlemen,
meat.
I hate to do it, but we are coming towards the end of this episode. Henry, I think it's fair to say there's plenty to talk about with Tony. We might have to do a second episode.
And he's got the metrology handbook experience. So, Tony,
That'd be great.
what chapters in the metrology handbook so people know?
Yeah, what did you contribute?
Oh, what did I contribute? I did a lot of editing with Heather. So she would share a lot of chapters with me, and I'd go through and look at how that was written and suggest changes. I'd say that the chapter that got my biggest contribution was the environmental chapter.
Okay, which deals a lot with pressure then, so that makes a lot of sense there.
That was probably my biggest contribution to the book, was the chapter on the environment.
Tony, the other one we like to ask all of our guests, what's the weirdest thing you've ever measured? The funny one we talk about right now is Howard Zion came on and said he measured a wobulator. So what is the weirdest thing you've ever measured?
I assessed a lab who had a hook gauge. It was a way of, it's a primary standard for differential pressures that had these little vials of water in a dimensional where you would set up the pressure, and it was in inches of water, and you would measure with a micrometer on the height of the fluid.
Yeah, the spindles.
I'd heard about these things, never even saw a picture of one, and they had one in their lab, and I was like, do you still use this? They're like, oh yeah. I'm like, show me. I want to see this method.
I've seen
pretty
them
cool
before. Those are crazy. I'm curious how many people listening have ever seen one, because they're a little antiquated. I mean, aren't they still valid though? I mean, they're not necessarily antiquated.
They are. What makes them a little bit difficult for traceability purposes, you got to be able to convert units. So not everything that you test. So like most of your sensors that you got out there that do measure in inches of water, they're not using water. So they've got they've got a board on tube, or they've got a crystal. They're doing the electric effect or something like that. And it's just a unit of measure. Inches of water, well, it depends on the temperature of the water, determines the density of the water. So there's different ways of changing the height without ever changing the pressure. Change the temperature, you can change the height. You can increase it and raise the height without ever raising the pressure. So you have to be measuring these other constituents. You need to have, as an assessor, I would want to see, so you've got your reference standard reading, you would have the device under test reading. I would also want to see temperature, humidity, and barometric pressure, because air density's got to matter on that, because you actually are using water. And for those units, so you can't really control to a high degree the temperature of that water and the density of the air that you're doing the test in. So if you're testing something that, let's say, is an inch of water at 4 degrees Celsius, you have to correct to it. So you can't just do a comparison, because the water that you're actually using isn't at 4. So now you're apples to oranges. That's not a real comparison. You got to do a conversion. You'd have to be putting these numbers into a computer with an elaborate formula to do the correction on that. So it takes a little bit.
I know some labs that I hope are listening right now. You better take a look at your setup, because I know you're doing 0 of that.
Or call me, and so I can be educated on being a better assessor if I'm wrong.
No, that's perfect. Actually, that leads in great.
That is great.
Tony, what is the best way to get a hold of you, if anybody? Do you want people to just reach out on LinkedIn? Because we don't want it to be too invasive.
Sure. LinkedIn is probably the preferred way. LinkedIn.
Let me give you all his personal cell phone.
It is.
Imagine the text coming through.
Okay, everybody, it's 867-5301. So you guys got to guess the area code, and if Jenny answers, tell her.
We're dating ourselves.
Well, Tony, I can't.
867-5309 is Tommy Two-Tone. Right. Yeah. That's
right.
Tommy Two-Tone, and there's no area code, so you guys figure it out, play it, and see if Tony answers. He probably won't.
Well, Tony,
go to LinkedIn.
Tony, thank you again for coming on. But having the great guests and bringing the insights that you have is invaluable, especially the people that are learning this industry. So hopefully people can learn from some of the mistakes others have made previously, right?
Absolutely.
We all make them.
And I would not be where I am without the mistakes that I've made in the past. You got to be open to the mistakes. You got to be open to the fact that sometimes you're wrong. You got to go into conversations not thinking that you're the smartest one in the group. It actually helps to think you're the dumbest, and you got something to learn.
Open up those ears, right?
Yeah. Yep. Listen to the question. It's better to understand what's fully being asked, not to prove how much smarter you are. That's like
this stuff is hard to comprehend. It's not easy.
It is.
It's complicated.
Yeah. And what the problem is, sometimes you get judged today by the stuff you did 3 years ago, and we're all much smarter than we were 3 years ago. So that's
the last annual conference that I went to for being an assessor. I learned stuff about pressure I'd never known.
Yep.
No idea. Zero gauge. How do you make that traceable? All I did was open both sides to atmosphere. How's that traceable? What are you traceable to? Atmosphere? Not saying it's not an accredited cal, but you're not traceable. 0 PSI. Well, what's traceable about that? How do you make it traceable? Never thought about it.
And with those questions, we will see you the next time. Thank you for listening. Thanks,
right.
Henry.
See y'all. See y'all.